It's my great, great pleasure to introduce Justin Solomon, another member of MGGG. Justin was the last of us four to join MGGG. Basically what happened is he wrote us to say, hey, I'm around, here's my expertise, I'm interested in what you're doing. We invited him to one of our meetings figuring, okay, we'll talk to him for an hour, then we'll politely ask him to leave and proceed with the meeting. And at the end of the hour, we just sort of all looked at each other and we're like, this guy's a keeper. We're not asking him to leave. and now he's stuck with us. All right, so Justin is an assistant professor in the Computer Science and Artificial Intelligence Laboratory at MIT, where he runs the Geometric Data Processing Group. His research group studies problems at the intersection of geometry, numerical methods, and large-scale optimization, with applications to fields from computer science, graphics, to machine learning, to now redistricting. Thanks.
All right. Excellent. It's such a pleasure to talk to you guys today and to share some ideas that I have that are maybe a little bit of a bad cop to the good cop that we just had in the previous lecture. One thing that I should warn you guys, as you kind of heard about from Mira just a moment ago, I'm relatively new to this particular world, and I want to kind of preface my talk a little bit with that. A lot of what I'll be telling you about are things that computer scientists might already know, so if you have a technical background, you might kind of think this is a little bit basic, but I think these are really important ideas to highlight on their own and tell you. And secondly, that a lot of this is very preliminary work. So my hope is to get a discussion going on some connections between what I view as a very relevant discipline to the world of redistricting. And my hope is that you guys will come back to me with all kinds of feedback about all the things that I don't know. And hopefully we'll have a nice conversation about ways that we can work together. To give a tiny amount of background, as Mira mentioned, I'm the PI for the Geometric Data Processing Group at MIT. And of course, if anybody just likes geometry problems, I encourage you to come talk to me about just about any problem you have in the geometry world. But roughly, our group studies things that are at the intersection of the theory and practice of geometry, right? So on the one hand, we're making use of mathematics from areas like differential geometry, optimal transport, which you'll hear about this afternoon if you come to our math session. And on the other hand, we interact quite a bit with people on the application side, everywhere from computer graphics, computer-aided engineering, to computer vision, and hopefully to redistricting. I think it's no secret, of course, if you look at a lot of these redistricting problems, that at a very base level, it's a geometric challenge, right? And when we're talking to people that are carrying out these redistricting challenges, for example, what you saw in the previous talk, really, these people are solving a problem that's largely geometric. Obviously, there are so many other axes on which we're judging these districting plans, and I think we've heard both the legal perspective, the mathematical perspective, and so on. But somehow, at the end of the day, we have to draw shapes on a map. Right? And so my goal today is to tell you about the shape side of that and to share some perspective that we have from the sort of computational geometry world in terms of sort of principles for how to engineer these kinds of tools. Now, after this fateful meeting with Moon and Mira and Ari, I went back and did a little bit of reading on my own. And what I discovered was that really, if you look at the literature, and when I say literature, I mean in a very broad way, everything from news articles to academic literature on redistricting, it sort of falls into a few different categories, right? So on the one hand, there are these sort of popular science articles, for example, that this computer programmer solved gerrymandering in his spare time. And this is a very hopeful title, right? That somehow computer scientists are going to walk in and tell us what we're doing wrong in the redistricting world. Incidentally, it is not my intent to at all criticize the computer programmer who they're talking about in this article, but just to tell you sort of two very contrasting opinions on the same problem, right? On the one hand, you have these sort of popular articles that tell us about how exciting it is that computers are going to solve redistricting. On the other hand, if you dig through the academic literature, one thing you'll find very quickly are phrases like what I've underlined on the bottom right, that somehow the redistricting problem in general, and even many simpler redistricting subproblems, are likely to be intractable. Now, intractable is a fancy computer science word for like, we don't think we can do this. Right? And so somehow there's this totally reasonable question, which I would imagine a lot of people from the outside looking in, especially if you don't have a computational background, might ask, which is, well, which one is it? Can we solve gerrymandering and just do it on our laptop? Or is this somehow fundamentally a computationally hard problem? Like, where can we trust computers in the redistricting process? And so the question that I'm going to kind of pose today and give a few initial thoughts about is really, what is the role of computation in political redistricting? And notice, when I say this, I'm using the word role, and I think I'm using the phrase quite a bit, very broadly, right? That it's not just, giving a computer a map and saying, generate for me a districting plan, but it also includes, for example, computation in tools like District Builder, where really somehow the computer is acting as a partner in the districting process. And again, that's really what I'd like to emphasize today, that somehow we're partners in generating the best possible map. Right? Now, on the left-hand side, of course, we have a CPU, and computers can do calculations at 10 to the 9 computations per second, right? They can add, subtract, multiply, divide very quickly, but they have no legal understanding, and as of now, at least in the research world, we really don't have a way of giving computers sympathy. On the other hand, when we look at redistricting committees and other sort of political, legal organizations that study these problems, I'm not sure how many computations per second they can carry out, but they have a very strong legal understanding, and they're sort of potentially, sympathetic to the different needs and push and pull and demands of the redistricting problem. Right? So really, what I'd like to advocate is not to view the computer as the redistricting tool that we should trust 100%. I also think the same thing about humans, but really that these people should be partners in the redistricting process. And when I say partners, one thing that we'd like to ask is sort of, there's a whole spectrum of different ways that you could imagine using a computer to help you carry out redistricting, right? And one of the big things that we do as computer scientists is look at different types of problems and ask the question of how easy or hard would it be to solve that problem on a computer. And roughly the spectrum that you get looks something like what I've shown you on this slide here. That on the one hand, it's very easy to carry out certain tasks. For example, you can visualize districting plans, you can collect data, you can make spreadsheets, GIS, and so on. And we saw some really great examples of that in the previous talk of really effective ways to visualize and understand the redistricting problem. There's a more gray area of taking existing districting plans and improving them in different ways, evaluating different compactness scores, sampling the space of possible plans. We've heard about all these things this week. And then finally, and I'll expand about this in a little bit, there's a really clearly difficult problem, which is I give you a map and all the criteria I could possibly want to evaluate the quality of my districting plan, and I just want a computer to walk in and generate it automatically. And that's sort of too bad in a sense, right? Because, we view computers as these unbiased machines that can, solve these problems without all the push and pull of political interests. Of course, there's some question as to whether your code can actually do that. Like, for example, whether the person writing your code has their own interests that they can write into your computer software. But that aside, the optimism that, for example, that Washington Post article is giving is sort of indicating that the computer is a good judge here. But on the flip side, unfortunately, it's clearly intractable to just hand the computer the districting problem with no additional information and expect it to do at least an optimal job. So today what I'm going to advocate for you guys is that when we're sort of considering different roles for computation in the redistricting world, there are a couple different desiderata that we should really take into consideration very carefully. In particular, I've sort of classified them in two sides. On the one hand, we need to talk about stability. This is an idea that's largely from the world of numerical analysis, if you're a technical person, which is that if I somehow perturb the information or the input to my redistricting tool, I don't expect the output to change that much. And I'll show you some interesting examples where that actually doesn't happen in redistricting algorithms. And on the other hand, we'll talk about efficiency, that if a piece of computer software can solve the redistricting problem, but it takes a ridiculously long time, for example, after the election takes place, then somehow we haven't really done anything useful, right? And so my, maybe bold, maybe not so bold assertion for today is that any measure of compactness or fairness that we can't compute in a stable and efficient way is not useful. And similarly for any really piece of software that we use for the redistricting problem. Okay, and when I talk about this, one of the things that you'll notice, and somehow one of yesterday's speakers, she kept saying, like, well, I want to say something positive, and then she'd say something negative again. I'm going to do something very similar, which is, when having written a lot of sort of geometry-related software, one thing you learn very quickly is that anything that can go wrong will. And geometry is a really great area for seeing all of the bugs in your code ridiculously quickly. And so what I'd like to advocate is somehow a pessimistic approach to developing software for redistricting, that we really have to consider every possible case and every possible adversary when we're engineering tools for this particular problem. And why is that? Well, on the one hand, for example, we have 435 congressional districts. That's, from a geometric perspective, just a lot of shapes. There are a lot of weird things that can happen in that set. Also, Wendy touched on this yesterday. There's, roughly 11 million census blocks. And let's say I want to consider every possible partition or way of permuting or understanding, combining the different districts. That makes a ridiculous number of possibilities of variables that you can optimize over. Now, of course, Wendy suggested, and she's absolutely right, that, of course, this is a little bit facetious. A large number of this 10 to the 3 million options can be eliminated very quickly. But, if you even eliminate an order of, 1,000, 1 million from any of these numbers, you still haven't done that well. Right? And so to give you, some baseline for comparison, the sun is going to swallow the earth in about 10 to the 9th years here. And we're talking 10 to the 3 million possibilities for your optimization problem. So unless you have a really fast computer, we have to be a little smart about this. Okay, so today, what I'm going to try and do is give you a taxonomy of potential benefits and limitations of different computational redistricting tasks. So rather than tell you about specific types of software, I'm going to kind of categorize the possible things you could do with a computer and tell you a little bit of the sort of drawbacks you should be aware of as we really go out and start to engineer different ways that we can view the computer and the human as partners in the redistricting process. And I've kind of organized this from considerations in the small to considerations in the large. So we're going to talk first about very small issues of perturbation and stability. Then we're going to step back a little bit to understanding what can happen when you have noisy data. Then we'll step back a little bit more to, okay, now I'm given my data and I'd like to solve some kind of inference problem on top of it. What can go wrong and what efficiency issues we have. And then we'll conclude with, time permitting, a list of what I view to be open challenges in this space. So we'll start by talking about stability. Now, for those of you who aren't familiar with the computational literature in this area, roughly, when I talk about an algorithm being stable, what I mean is that when I make a small change in the input to my piece of software, I expect there to be a small change in the output. And if there isn't, then there better be a good reason why. So let's give a really small example to start with. So let's say that I have some two-dimensional landscape, and I place a ball on that landscape, and I just ask you, if I let the ball roll, where's it going to end up? Yeah? So if I have a piece of software that that can predict this piece of information, and I give you this ball position on the right-hand side here, obviously we're going to, the ball will roll into the little sink on the right. Hopefully you all believe me there. And this is somehow a stable calculation in the sense that if I perturb the starting point of the ball, right, no matter what, I get the same, in this case, exactly the same output, right? They always predict the same location for where it's going to roll. On the other hand, let's say that I place the ball on the top of the hill, and I ask where the ball is going to end up if I let it, I let physics take its course. Well, of course, there's a really clear instability here, right? If the ball tips a little bit to the left-hand side, it'll end up over here. If it tips a little bit to the right-hand side, it'll end up over there. And that's really the high-level idea of stability, right? That there's certain calculations you can do that are resilient to noise and resilient to estimation, rounding, and so on. And there are other calculations for which that's not the case. Now, stability is one of the key considerations whenever you develop any piece of geometric software. And as a great example of that, I'll tell you about one really simple problem in geometry, which is I draw a shape, and I want to know if a point is inside of that shape or not. This is obviously relevant to the redistricting problem, right? I have somebody's address. I want to know if they're inside of a district or not. Now, one of the standard algorithms for this problem is very simple, and hopefully even if you haven't seen it before, I can convince you that it's true very quickly. So let's say that I'm at this red point here. What I'll do is draw an arbitrary line out of that red point in any direction and count the number of times that it hits the boundary of the shape that I drew. So in this case, it hits the boundary 1 time. And notice that this point's on the inside. And now let's say I drew a different arbitrary line, for example, this one going to the bottom right, and you notice that it hits it 3 times. Well, what do we know about the numbers 1 and 3? Both of these numbers are odd. And in general, this is the case, that if you count the number of times this ray hits the boundary, even if you have kind of a non-convex zigzaggy shape here, if that number is odd, you're on the inside. If it's even, you're on the outside. One way to think about this is that sort of every time you hit the boundary, you kind of flip from whether you're on the inside to the outside, so you want an odd number of times. And this is really the standard algorithm for just figuring out if you're inside a shape or not. So let's say that I have, a voter's address, and I'm trying to figure out if they're in the 6th congressional district here in I guess, outside Atlanta. Yeah, and maybe this guy wants to live, I think this is a highway here, this blue line, and they want to have a nice highway view, and so they've situated their house right at the end of this little line segment here. And now, of course, I can carry out this test, and it's very clear from this picture that their address is in the inside of the 6th Congressional District. But let's say that I'm a little bit lazy about writing my piece of software, and I say, well, it doesn't matter which of these lines that I choose, so in a sense, like, I might as well just always choose the line going straight up. Yeah? Well, what happens here? Well, this line intersects the boundary not at a point, but on an entire line. Yeah? And in particular, let's say that line's a little noisy. Maybe it goes in and out and in and out and in and out and in and out. And just because of rounding or other issues on your computer, God knows whether you're going to be in the inside or the outside. So this poor gentleman may actually not have a political district, right? You might have your software, it tells you, because here you just made one mistake on the inside telling you, you know, he's not inside of this district, but obviously he's not inside of any of the other ones. And now we're in a little bit of trouble. And really, obviously, there are easy ways to fix this particular issue. But what I'm trying to convince you is that geometry, or I guess Moon gave me a hard time, computational geometry is all about border cases, right? And that whenever you write a piece of geometric software, it's not enough to kind of talk about what happens almost all the time. You really have to consider every possible case. Right? Mathematicians love to use this phrase, which somehow sounds very fuzzy from the outside of mathematics, where we talk about things holding almost always. I remember when I started as a math student, I would read that and think, well, that doesn't seem very precise. It turns out there's a definition for that. It's not enough for things to hold almost always in our case. We need to have 100% certainty that our calculation that we carry out is going to give us the result that we expect, because the reality is that there's a ridiculous number of things that can go wrong and do go wrong, specifically when you consider the shapes of districts, tracts, census blocks, basically anything. And so I worked with our intern Asaf to identify a couple examples here, and I'll show you some really crazy things here. So for instance, obviously there's no secret that political districts, tracts, and so on have very non-convex shapes. Sometimes they can even look like slivers. Apparently this is a piece of the Charles River on the right-hand side, which surprisingly to me actually has a non-zero number of residents, according to census data. Maybe it's a houseboat. Or for example, here we have the tracks in Texas, and you can see hopefully you can see in the back, I know this projector is a little blurry. Some of these, first of all of these tracks have axis-aligned boundaries. Right, so remember I proposed, if I wanted to figure out if a point is in the inside or outside, I draw a line straight up. Well, in general, that's got as high a probability as any line of satisfying the boundary cases I worry about. But the reality is that shapes that we look at when we're considering congressional blocks, congressional districts, are not random. They're designed by humans, and humans tend to design shapes in a particular way, right? Another example of something that can happen that we might not think about as software engineers is disconnected regions. So for instance here, this is tract 980101 in Massachusetts. It's on the coast, and of course there's lots of little islands and so on. Right? And finally, you know, even if you step away from geometry and just talk about topology, remember topology is this area of math about how stuff is connected. You can have really bizarre topology for things like tracts. So here, this is a tract in Texas with a hole in it, right? In other words, I can draw a loop around this hole, and I can't kind of shrink it to a point without leaving that tract. So for instance, if I ask you for the perimeter of this tract, it's like, no, you have to be very careful how you write your software for doing that, because it's not just one curve, there's two. So all of these things can and do happen. I can't emphasize that enough. And so writing a piece of resilient software from the ground up is really critical for these sorts of tasks, right? And so for instance, I'm sorry, there's one more here. I'm sorry, the color isn't great for reading the text on my slides. That if you look at the set of census tracts, you might view them as kind of having equal populations, right? Like this is one way to simplify some of your calculations. You do math on the tract level. But of course, that assumption is false, right? This is what we call a discretization artifact in computer science. We've taken the map of the United States and made it into little discrete pieces with some assumption on sort of how they're distributed. But in reality, it might not be possible or practically possible to carry that out. So in the geometry community, this is one of these concerns that just comes up over and over and over again. When we do computational geometry, it's not enough to just consider software that usually works. We have to consider every possible case, right? And if you look, for example, at the documentation, so this is CGAL, the Computational Geometry Algorithms Library, which is one of the most common tools for writing geometric software. And you read their documentation, you'll see that they sort of have a lot of high-level explanations of what can go wrong. And they're really kind of analogous to what I've already shown you here. In particular, what they tell us is that in geometry, it's not like we're computing numbers, right? We're not just computing numbers like radius, perimeter, or whatever, but we're really computing structures, right? Holes, triangulations, and shapes, and so on. And when we ask questions like, is a point to the left, to the right, or on a line through two other points, these questions have no answers that are slightly off, right? There's no notion of like perturbing and being stable. You're either to the left or to the right. Right? And so this is primarily a combinatorial problem, not a numerical one. You have to make a discrete choice. Yeah? And so there's lots of different ways of addressing this. And so I'd like to highlight, this is going to be one of these times, remember I told you this talk is very preliminary, and we're talking about lots of different ideas for how to make these sorts of calculations robust in the context of redistricting. Some things that you could highlight would be, maybe you give some confidence bounds to your calculation, right? Like maybe I say, I can't actually tell you whether this guy is in this district, but I can tell you with some certainty that he's close to the boundary and that I think he's in this district. Right, so this dates back to this early papers called epsilon geometry, where they say, like, I'm epsilon collinear, meaning that I can't actually tell if 3 points are on the same line if my numbers are a little noisy, but there's some region away from which I'm pretty confident that they're on one side or the other. Or one thing that you'll hear about if you come to this afternoon's math session is a theory of mathematics called optimal transport, which is all about sort of coupling probability and geometry, right? So if I have a noisy measurement and there's nothing I can do about it, can I still do some geometric calculation that I can rely upon? So as sort of the first principle I'm going to propose to you guys for computational redistricting is that geometric measurements at the very bottom level in redistricting software must be provably robust. Because if they're not, they might actually be introducing some bias that's really, really hard to detect and understand. And so as an example of some people that do this really well, one thing I wanted to highlight, and I don't expect you guys to read this, by the way. It's like one of these blocks of text you should just appreciate for being a block of text. I come from the numerical analysis world, right? Like the kind of number crunching on computer world. And one thing that we have to worry about it is, of course, your computer can't represent every possible number. There's a lot of those. And so what we do is we have to do things like rounding and deal with precision. So maybe I store numbers up to 2 decimal points, right? Of course, the issue is if I multiply 2 numbers with 2 decimal points, I can get a number with 4 decimal points. Right? And so somehow I've already kind of overflowed the amount of space that I've reserved for a single number, and so I have to have some procedure for rounding up or down to account for that. Right? So if you read, this is the IEEE floating point precision, double precision floating point library. This is essentially the basic standard that computational people have for how to store numbers with decimal points on the computer. One thing that's just worth appreciating is how careful these people are to be fair in determining how they do calculation, right? So this entire paragraph on the right is telling you how to round to numbers if you overflow the number of decimal points you have. And you can see that the rules that they come up with are like not imprecise. And the reason for that is that what's going to happen is that, Intel and AMD and NVIDIA and all these different companies are going to go out and implement this standard, and we want it to be 100% reliable no matter what computer you use it on. And I would argue that this is exactly a property you'd like to have for any redistricting software that you want to engineer. So obviously what I'm talking about right now is on the very, very small scale, right? We're talking about errors that happen in the last couple decimal points of a measurement. And the reality of software like GIS and geographic information is that the errors that you see are not in that regime. They're actually in, like, somebody made a measurement wrong on the Earth and they're off by feet instead of like 10 to the 9th feet. Right? And so these same concerns about stability extend to that case as well. So as a simple example, and one that I think has already been ragged on a little bit in this conference, I thought I'd highlight one measure of compactness of a district. This is called the Polsby-Popper score. I would imagine at this point most people in here are familiar with this idea. But roughly, if you take a shape and you take the ratio of area to perimeter squared, then you can show that this is, you multiply it by the right constant on the left-hand side. This number is bounded by 100%. And the reason for that is that somehow a circle is the shape that uses area the most efficiently, right? I bound the most amount of area inside of a circle for a given amount of perimeter. And so this is some way to measure compactness, right? As you deviate from this ratio, right, your score decreases. Essentially what you're saying is you have some long squiggly district with a lot of perimeter. So one thing we might do is say, great, so this is one way to measure compactness of a district. And so I write my piece of software for doing that. And indeed, this is something that's implemented in GIS. This is easy to try. And here, what we've done is highlighted 3 different states of Maryland here. And these are just from 3 different files that we downloaded from the census that are at different resolution. And hopefully you can read on the bottom row of this chart here exactly that Polsby-Popper score, this ratio of area to perimeter squared. So on the left-hand side, we have 12%. In the middle, we have 7%. On the right-hand side, we have 4%. This should really scare you. Do you see that? That essentially, if I'm using this number as my judge of whether a district is compact, this number has more dependence on which map I used than on anything having to do with compactness. Right? And what's the reason for that? Well, if you take a look at these squares that I've kind of put on top of these shapes, you can see that these are different resolutions. So we capture sort of the geography of the coastline in different fashion. Right? And so this is what's called the coastline paradox, which Moon also mentioned in her talk. Right? That you actually can't really measure the length of a coastline in any meaningful way. Right? And because of these types of measurements are also unstable in a very different way than just rounding numbers, but I would say in an almost more pernicious way for the redistricting problem. Somehow you can engineer a score for your map. You know, if I'm a politician, I'm trying to say my map is really compact, I'm going to download the best resolution that supports my claim. And that's something that we should not allow to happen. Yeah? And these things, you know, these kinds of instabilities happen in a lot of different data that we see from the census and other organizations that we care about. So for instance, here we have in red the boundary of a district and in black the boundary of a census block. In reality, these 2 things in this particular map are supposed to be aligned, but you can see that somehow the resolution of one is different from the other, and so these 2 lines diverge a little bit, and you could have 2 different measurements depending on what map you use. Or we've heard a little bit, for instance, in talking about whether we can measure gerrymandering based on looking at the graph, right, like connectivity, how different districts are adjacent to one another. And one really critical question to ask is how stable is the construction of that graph, right? How stable is it to measure if distances or districts are adjacent? And the answer is not very. Right, so here I've given you a counterexample. So these 4 colors are 4 different districts, and I've drawn a red edge anytime that these 2 districts are adjacent. Right? And you can see that I've inserted little triangles in different places on the inside where these things meet at a point. And depending on how I perturb these triangles, I can get different connectivity for sort of the adjacency structure of districts. Or on the right-hand side, in this case, you know, the 4 things meet at a point, and it's not so clear whether I should have these things meet at diagonal or not. Now, this isn't a criticism of what Moon proposed in her talk in terms of discrete curvature, but just a warning that as we construct this graph, we have to be quite careful about what value and ideas we ascribe to the edges here, and to make sure, again, that if a combinatorial change happens, if there's a flip, right? This isn't like a small perturbation. This is like a 1-0 change. That really, if our measurement of whether a map is fair or not also takes a 1-0 change, then we better understand why and justify that was the right thing to do. And this isn't just like some goofy example that I've drawn for you to scare you. For instance, here I have the Ohio 2011 districting map. And you can see there's some really crazy adjacency things that happen. For instance, here, this green and blue district kind of barely touch each other at about 4 or 5 points. If you zoom in really closely, you'll see that sometimes there's this little narrow thing separating them. But somehow, you know, if your measure of fairness depends on whether you cut that little narrow piece or not, this is a little bit suspicious. So if we step back a little bit, there's so many sources of instability here. Right? There's the idea that maybe your map is projected wrong. Of course, your computer screen is flat and 2-dimensional, but the world is round, and we have to account for that in a particular way. Maybe you have inaccurate measurement equipment. Maybe things just change over time, right? I mean, the census doesn't happen every day, and people move and boundaries change, and we may not have the most up-to-date information. Maybe your map resolution is off. By the way, hopefully you guys know what resolution is. When you have, for example, if you have the state of Maryland where we have these 3 different images, these are like 3 different levels of accuracy for sensing the geography, and these are called resolutions. Or maybe there's a security limitation. So like, I live in Area 51, and I don't want people to detect the geography of my aliens, and so I limit the resolution of GIS software inside of that little region. So all of a sudden, my calculation in that little spot is less accurate than everywhere else. Or finally, in the most pernicious of cases, maybe there's even some political control on the procedure of data gathering, right? I want to engineer maps to give the best possible score for what I care about. So if we step back a little bit, what I'm trying to advocate for you guys is that we need to be super careful as mathematicians and engineers to come up with measurements. And when I say measurements, I mean derived information from the maps that we compute that are stable. Now, of course, if you talk to a mathematician and you say, okay, I want the most stable possible measurement, what do you think they're going to tell you? Well, if you think about it for a second, there's one really stable thing to do, which is to say, no matter what, I'm going to always tell you that a district is gerrymandered, or maybe the other way around, whatever. This is incredibly stable, right? No matter what I do to x, f of x doesn't change. But in sort of the parlance of the machine learning world, we would say that this is not informative, right? It doesn't tell you anything. So our second principle here is that fairness measures must be stable and informative. So as a math guy, I can't help but do a tiny, tiny bit of math in our talk, and then we'll step back and draw pictures again. One thing that we could do to actually talk about and formalize this idea of stability is something that I've tried to illustrate for you here, which is that roughly if you make a small change in your districting plan, like on the upper left, on the upper row here, then you expect a small change in your fairness measure, right? So here, I'm thinking of f for fairness, right? So f as a function takes in your districting plan and gives you some number, where maybe that number is big if you have a lot of gerrymandering and small if it's not, or vice versa. So what does this imply? This implies that we need kind of two ingredients for a formula like this, right? We need some way of measuring similarity of districting plans, right? Some distance measure saying like these are similar, so we expect it to be stable under this perturbation. And then we need some way of measuring similarity of fairness measures. The second one's pretty easy. That's called subtraction. But the first one's a little tricky, right? And in fact, I'm going to pose as a question to the mathematicians in this room what makes the most sense here. So I can highlight a few. One, for example, is called the Frichet distance. The idea here being that, like, let's say I have 2 pens, and I can draw the state of Maryland with my 2 pens. Right? So I can trace through them with any velocity I want. And what I want to do is measure how far apart do those pens get at any point in time. And then that's sort of some measure of how different these two guys are. So probably the Frichet distance would detect this little sliver on the bottom left-hand side here. Another measure of distance might say, no, the boundary of the state of Maryland is somehow a rubber band, and the distance is the amount of work it takes for me to stretch the rubber band from one post to another. This is something called the killing energy. I promise you this is kind of a scary word, but it actually is named after a mathematician, which is unfortunate, by the name of Wilhelm Killing. Happens to be something from my research, so I thought I'd highlight it. We use it in the computer graphics world quite a bit. I bet you guys didn't expect to see 3D cows in this talk. So in general, once you have a measure of how similar districts are, right? And what you'd like is, as I make a small change to a district, right? As you know, if our similarity measure is small, I want our fairness measure to change a small amount. There are a lot of different ways to formalize that in mathematics, right? So the typical one is something I've highlighted here. This is the K alpha Hölder property. I promise this is the last equation we'll have, and then we're just going to draw pictures. That essentially says if I have the change in my fairness measure, that's on the left-hand side. Here's C1 and C2 are like 2 districting plans, is upper bounded by some multiple of the change in my boundary, right? So in particular, as the change in my boundary goes to 0, right, as plans become more and more and more similar, right, I would expect my fairness measure to have that same property. Again, this is just something I'm putting out there as a straw man that I expect you guys to totally tear apart. Right? In particular, I would imagine there are certain cases where some little change happens and you really expect your fairness measure to take a big jump. And it would be interesting to think about exactly what those are. Okay, so now we're going to proceed to tractability. Right? Remember, I promised we're going to keep stepping farther and farther back in terms of the scale at which we look at our problem. Right? We started by talking about just dealing with sort of small numbers and perturbations. We stepped back a little bit and talked about noise in our measurement. Now we're going to say, okay, fine, we have all these noisy measurements. I'd like to make a piece of software that sort of deals with all of those at the same time and extracts something like a districting plan. So in computer science, when we talk about something being tractable, what we mean is that it's accomplishable in a reasonable amount of time. Right? In other words, you know, if I have a laptop, or maybe I even have blue waters, like what Wendy was talking about yesterday, you know, and I only have so much time on my clock for my piece of redistricting software to converge on a good plan, do I expect to be able to get something in that amount of time? Yeah, this is a question of tractability or complexity. So, that Washington Post article is really somehow heartening, right? It's telling us that we can solve gerrymandering. But the sad fact is that some problems are just inherently difficult or even impossible to solve on a computer, right? The computers aren't just the be-all and end-all of mathematics and computation, but rather they're sort of enablers of a different type of computation that may or may not be useful in the redistricting process. Right? And so when you read in the computer science literature and you learn about things like complexity theory and algorithms and so on, really what they're trying to do is to look at a problem, not necessarily a piece of software, but a problem, and kind of develop an intuition for, do I expect that I could solve this problem on a computer? And so sort of what I'd like to advocate for you guys is that really it's worthwhile to kind of develop some theory of complexity that's related to these different redistricting problems so that when we see a piece of software out there that claims to do some different task for redistricting, or if we set out on an engineering project to solve one of these problems, to kind of know a priori whether we expect to do, exceedingly well and solve the problem, kind of sort of well and get a good initial guess that people can kind of work with in the legislature, or whether we expect it to be doomed to failure from the start. Right? And that's really what complexity theory is all about. So to formalize that a little bit, let's say that I wanted to make a piece of software that automatically extracts a set of districts from the census blocks. One question I might ask is, as I increase the number of census blocks, how long do I expect my computer to take to extract the best possible plan? Right? And what complexity theory is all about is identifying this kind of shaded region here where I don't ever expect my curve to sit in that area. In other words, that there's some lower bound on the amount of time that it takes to solve this problem just because the problem is hard rather than because I'm bad at writing software. Hopefully the distinction makes some sense. And so one thing to note is, of course, I can be above this. For example, if you ask me to code, because my background is largely in mathematics, my code will be above this line because all my code is slow. But somehow, fundamentally, there's something about this problem that tells me that I don't expect there to be a piece of software that solves it. So at this point, I'd like to highlight something that was mentioned in Wendy's talk, but I think is worth calling out very explicitly. So let's be clear here. Any piece of software that claims that it extracts the best possible districting plan under any reasonable metric, I'm sorry, red is a little hard to see, also solves the most famous open problem in computer science. Let me repeat myself. Any piece of software that tells you they make the best the best possible redistricting plan also solves the most famous open problem in computer science. I think most people at this point have at least seen the letters P and NP, even if they don't understand what this problem is. But roughly in computer science, there's a really fundamental problem, which is, are there classes of problems that we just can't solve in a finite amount of time, or in a reasonable amount of time on a computer? In other words, that scale kind of well, right? As I increase the number of my census blocks, what does that plot look like? Right? If that plot is like exponential and just takes a ridiculous amount of time for even small problems, then somehow I don't expect to do very well. And that's this class of problems we call NP. Right? And we actually don't know. And when I say we, I mean myself, my colleagues at MIT, the whole computational community, whether those problems, like there's some really, really slick algorithm out there that we just haven't found that will make these problems solvable, but we expect that's not the case. There's something fundamentally difficult about these things. So if you give me a piece of software and you say, I make really, really awesome, like the best possible redistricting plans, I'm going to say, that's really, really cool. You should present that at the Theory of Computer Science conferences because you're going to get $1 million from the Clay Mathematics Institute. Now, and in fact, my conjecture is that it's not just that optimal redistricting is hard, but that it's ridiculously hard. And in particular, one thing you might say is, okay, well, maybe it's not possible to get the best possible plan, but as a rule of thumb, I can do pretty well. And unfortunately, the computational literature actually says that that's not necessarily the case either. Unfortunately, I wish I had a little bit more time before this conference to come up with a theorem of my own, but instead I'm going to quote theorems from adjacent problems to the redistricting one. And even if you don't want to read them here, roughly what these say is that I can't just, it might not be possible for me to solve the redistricting problem optimally, but for example, getting any districting plan reliably within a factor of 1.5 of the best possible plan is equally difficult to getting the best possible plan. Do you see what this means? This means that this problem is not just kind of hard, like hard in mythology, but really practically quite difficult. The sort of principle that I'd like to propose to you guys, well, for one thing, if you're a computer scientist, please solve this problem would be great. But I think the more realistic request for everybody in this audience is that we need to be extremely careful about how we talk about computational redistricting. Right? It's one thing to have these cool, kind of popular science articles that tell us, that we can solve gerrymandering, but that creates really unreasonable expectations that are not defensible in court. Right? So if you put me on the other side of one of these pieces of software, it's very easy for me to create doubt. And that's not to say that this software isn't incredibly valuable, right? It may be the case that software that's very heuristic for extracting districting plans in practice works quite well. But if you use the word best or optimal or high quality even, you'd better be able to back it up, either empirically or mathematically. Again, this is not a criticism of the computer scientists in this article. I want to make that really clear. Okay. So that's our pessimistic story, and of course, there are a lot of positive things to talk about, which is sort of what can we do? And I think this is really where we should be focusing our efforts, right? So for instance, we can very easily analyze and compare and visualize and understand existing or potential districting plans, right? District Builder is an awesome example of this, where they talk to not only the computational community, but as you heard, to like the human-computer interaction world to really make sure that we're presenting these in a fair and understandable way. Another thing that we can do is at least, we might not be able to get the best possible plan, but we might be able to improve a plan. Right? So for instance here, maybe I have, this is the boundary between two districts, and I just say like, well, what would happen if I inserted this little triangle here? Would, by the metrics of fairness, compactness, whatever I have, would they improve or not? Well, if you think about it algorithmically, that's not too challenging, right? I can just compute it with and without, and if it's better, I keep it, yeah? And I can iterate this process. This is something that we call hill climbing in the computational world, right? That I can take something and I can just kind of try a change. If I'm happy with it, I keep it. If I'm not, I throw it out. And at the very least, this has the property that I end up somewhere better than where I started. Yeah? And we might as well put tools for hill climbing inside of these redistricting things, because maybe they can suggest to people that are interacting with these plans kind of non-obvious ways to make them better. Of course, when I say hill climbing, there's kind of a weird computation, or a weird problem that happens in this world that maybe doesn't happen when I just write something like f of x here. In particular, I have to decide which hill to climb. Do you see that? In the world of redistricting, there's so many different competing, I don't want to use the word interest, but competing optimization criteria that you want for a good map, right? Maybe you would consider the isoparametric ratio. Maybe you think about graph curvature like Moon has suggested, or dispersion, equal population, minority representation. Somehow every single one of these things has to be good for a good districting plan. But each one of these is its own hill, right? And it might not be clear that I can improve all of these axes at the same time, right? There's some trade-off. And so something that I'd like to kind of suggest that you Google as a cool search term. Originally, I wanted to talk about this, and then I realized that we're going to get in the weeds of some pretty heavy math if we did. There's a notion in this world of what we call multi-objective optimization, of something that's called Pareto optimality. And the idea here is that if I have not just one objective, but like 10, even in that case, there might be plans that suck. Do you see that? There might be plans that are just terrible on all 10 axes, and we might as well throw those out. Right? And so the theory of Pareto optimality is sort of saying, let's be conservative about what we say is the best possible plan, but at least not throw away, not throw the baby with the bathwater. We do have some hope of hill climbing that can maybe do better than what we have. Right? And so, for example, identifying a point on the Pareto set or on the Pareto frontier is something that is computationally tractable and something we might want to try. Something else that we can do that I was so excited to hear about from Wendy is sampling, or MCMC, right? This idea that we can randomly generate tons and tons of districting plans, and maybe some of them are good and some of them are bad, and this is going to help us kind of understand the space of possible plans. I think there's one possible sort of language issue that we should address and really think about carefully, again, when we talk about these methods. And indeed, I think the one time that they sort of appeared in court, this was a little bit of a problem, is that we have to be careful what we can promise when we talk about these techniques. In particular, whether we can claim that they're uniform. In other words, that they don't just sample reasonable plans, but they sample all reasonable plans with equal probability. I would argue that all the techniques that we have right now do not have this property. And one that's maybe a little more subtle, which is something we call mixing time. That we might say that these algorithms eventually can generate a sample that's completely unbiased and random from the space of all possible good plans. But the amount of computer time that it takes to generate that sample might be quite high. And if we stop our computer ahead of time, then we need to understand if we inserted bias in that procedure as well. Hopefully you guys can see what I'm communicating here, which is that there are insanely, insanely subtle issues here, right? That essentially even really innocent looking calculations can insert bias and in a way that's either completely innocent or even quite subtle. That we need to be aware of and kind of combat against, especially if we're going to codify any of these standards in law. So again, I would propose sort of thinking about this in kind of a hierarchical way, that there's really clearly easy problems that we can and should solve. Some of them are being solved by communities like District Builder and by our GIS team that's going to be meeting Thursday and Friday. There's some kind of gray area of things that we think we can help with, but we need to talk about them very carefully because we can't promise a lot, even if they're useful in practice. And then there are things that are just really hard. So again, sort of our principle here is that political redistricting standards must be designed with tractability in mind. Right? That it's not enough to just say, hey, I'd like in every single case to get the best possible partition of the map. Right? If we made a constitutional amendment that said that, it would be disastrous, right? Because it would put a lot on my plate as a theoretician to figure out how to do that. So again, to kind of summarize a little bit, these are just 4 basic principles of sort of, what I'm trying to give you is a framework for how to think about computational redistricting, evaluate claims that you see, and evaluate your own ideas in terms of what you can expect of a computer as a partner in the redistricting process. And what I would imagine, and what I'm hoping to hear from you guys, is sort of other ideas and other issues that you've seen in practice that we should add to this list. Right? These are just ones that come to my mind as a geometry guy, but I'm sure as lawyers, as politicians, as people doing redistricting, as people doing GIS, you've seen many, many more things that I didn't even think of. So in my last 82 seconds here, I'll really quickly identify some open problems that we think about and just scroll through. And maybe this is a nice way to kind of conclude our morning discussions as just things we don't know how to solve. In my case, in the computational world, for which we need input from everybody in this audience, both on the legal side, on the computational side, and on the mathematical side. To me, one of the biggest open problems here is how we can communicate the advantages and drawbacks of computational redistricting. Hopefully I've highlighted what can go wrong if you talk about this in an inaccurate way. And more generally, if we have a really complex computer system that we are pretty convinced is actually the right thing to do, that's actually not enough as engineers. We also need to be able to communicate that to the people that are actually drawing the districts and the people that are defending them. And that's quite a challenge, right? As anybody knows in the mathematical world, talking to other human beings is not something we like to do. And now, one popular thing in the computational world is this idea of machine learning, right? That somehow we can go out and collect a lot of data, and maybe that data can help us in political redistricting. My personal opinion is the answer is absolutely yes, that there are so many tasks for which machine learning is really critical in the redistricting process, but at the same time, we have to take it with a grain of salt. So for instance, one discussion that came up in one of the afternoon sessions yesterday was about explainable machine learning. Right? I don't want to just train a system that says yes or no, this district is gerrymandered. We also have to say why. Right? And so maybe the obvious question here is, I go out and ask 1 million people to just kind of rate 1 to 10, is this district gerrymandered? And I use that to develop my standard. I'm not sure that that's actually the right way to go from a legal perspective, although from a kind of understanding what people think about gerrymandering perspective, it's quite valuable. Another kind of cool math problem is to understand how complicated algorithmic problems are specifically in political redistricting, right? If you look at the arguments about why political redistricting is computationally intractable, they have nothing to do with politics, right? They're all to do with just partitioning. And it could be if you add some information about these problems, you actually get a more optimistic view than you might have in the most general possible case. And finally, one thing that just came up in the previous talk, and I think is really important, is this question of licensing, right? That if I write a piece of redistricting software and I'm convinced that it's right, and then I say, okay, great, you just email me your map and I'll email you back your districting plan, and here's this nice LaTeX paper that I'll give you with all the criteria I consider. That's not enough, right? You guys need to be able to see the code that I wrote in a way that's clear, understandable, and you need to see, for example, the hardware that I'm running my code on for redistricting to trust that I'm actually doing what I said. Right? And this is these ideas of open source and free software that I think are really critical for using these tools in practice. Right? Even, for example, visualization tools like District Builder. Right? You could imagine a really insidious visualization tool that maybe just kind of gently nudges you toward a districting plan that's just a little bit gerrymandered. Right? And these are the kinds of things that are really hard to detect unless you can look at the guts of this software. So with that, I really thank you for your time and with your patience for probably some problems that I've skipped. And I'm happy to answer your questions now. And then this afternoon, I'll be on much more comfortable ground. I encourage you to come to the math session and learn about optimal transport, which is something we know a lot about. So with that, I thank you, and I'll talk questions.
Thank you. Can you say a few more words about the concept of mixing time in MCMC?
Yeah, I think this is really critical when we talk about these tools. And actually Wendy had these really cool slides that were kind of zooming by, and one of them was a theorem that you might have seen. And that's actually, you should go back and look at that really, really closely, because it tells you a lot of the caveats here. So in general, you have some probability distribution. I'll try not to be too technical, but there's some like space that you're trying to sample, like the space of reasonable maps. Right? And on the other hand, you have some piece of software that's kind of walking around in the space of all maps, trying to kind of get to that space of reasonable objects. Right? And there's a little bit of randomness involved in the sense that there's this huge space of potential things that I want to sample from, and at the end of the day, I'm only going to generate, say, one. Right? And what I'd like to do is to at least say that I generated that one sample fairly, right? That I had equal chances of generating any fair map. Now, in reality, if you look at the algorithms for doing this, these are called these Markov chain Monte Carlo, or MCMC techniques. These are largely what's been proposed in this literature, although the genetic algorithm perspective that Wendy presented is a very different one. These MCMC techniques do not have the guarantee that you actually get a sample uniformly from that space. They have a guarantee that if I have enough computer time, the more computer time I put into it, the more random my sample gets. Right? But at the end of the day, I have to stop. So the idea of mixing time is that how much time does it take before I'm pretty confident that my sample is basically random, right, in terms of how I use my computer. And in general, what the theorems on MCMC say is there exists a missing time for which this is okay. But one thing we have to be quite careful about when we're using these tools is actually going through the really tedious process of computing that bound so that we're really confident that if we run our computer for 1 hour, that our sample is actually good. And I don't know of people, myself included, that have gone through that for these redistricting techniques.
We want stability in a good program, but in a competitive district, wouldn't a small perturbation possibly change the winner of the district? So is a stable solution potentially a non-competitive one? Can you clarify the kind of stability you're talking about?
That's a really excellent point. I would not say that it devalues what I'm telling you. What I would say is, you're absolutely right. Maybe you want instability in your vote. What you don't want is instability in your software. These are two very different things, right? It might be that your optimization criterion is actually that you would like, the vote that you kind of expect to happen to be close to 50-50 so that your different candidates have a fair shot. That's great. What you wouldn't want is, I have some measure of 50-50-ness, I don't know the adjective here, and that I'm not confident that that measure is actually right. That in fact, maybe my district is not really contested in any fair way, and I didn't get that because my measurement was bad. Hopefully this distinction, which is a little subtle, you can understand. That there's a difference between being confident in your software and its quality and its measurement, and being confident in the outcome of a vote. Right? These are two completely different tasks, both of which are very important for redistricting.
Will there be any summary released of what the GIS hacking group addresses over Thursday and Friday for those not attending?
Absolutely. If a tree falls in the forest and so on. Yes, I mean, our whole goal here is to generate tools that are actually useful for assorted tasks related to redistricting. And of course, part of that is actually getting people to use them, right? Right after this event, we'll be sure to release sort of just some information about, what worked, what didn't, what were the successful projects, and so on. Please remember that we have many more GIS tracks coming up around the country, and that many of the applications are still open. So if you're excited to participate, I encourage you to apply. And really, our goal is to make this be not just a 2-day thing that dies afterward, but an ongoing effort among engineers to sort of come up with needs, right? You'll see, and I'm happy to share some documents related to the projects that I've kind of collected from our various partner organizations for the GIS track. That these are not like things that I'm making up that I think like, oh, wouldn't it be cool if we did this? These are actual requests we've had from lawyers and people carrying out the redistricting for tools that would be useful. Also, I think we have some reporters that are coming and joining us Thursday, Friday, so you might see it even sooner than that, but I can't promise that.
In terms of transparency, do you think it's important to also have independent implementations so you can compare their outputs?
Yes, these are all great ideas. Right, so to kind of summarize for those of you who aren't familiar, one thing you might do is say, okay, I'm going to code up my software for redistricting, and then I'm going to give not my code, but a description of what it does to a colleague, and then ask them to implement the same thing and make sure they get the same result. This is actually quite valuable because it might be that I have even a mathematical theorem saying that, my redistricting tool is unbiased, but then I accidentally, I make some bug in my code and it actually introduces some bias completely in an innocent fashion, right? So if I have two people do it, the same way that, scientists talk about reproducibility, somehow that's one way to increase the confidence in these tools. I would say for visualization tools, maybe that's less important, but certainly for things that are kind of understanding the combinatorial space of walking around the space of maps, this is really critical.
How do we deal with the danger of machine learning algorithms learning our own biases?
This is a really good, I keep saying this, these are really great questions. Right, so for those of you who don't know, a machine learning algorithm only can tell you what you tell it. Right? In other words, like, at least with the current existing technology that we have, whether it's deep networks, SVM, whatever, I'd love to chat with you guys offline about the tech side. That's something I'm more comfortable talking about. Essentially, all of these tools take in tons and tons and tons of user input. They scrape the internet, whatever, they get a lot of data, and then their job is to kind of extract from that interesting conclusions. For instance, maybe I ask, one of the kind of fun things that we talked about for the GIS track Thursday, Friday is an app, where you swipe left, swipe right, whether you think a district is gerrymandered or not. I collect all of this data, and now I want to have a piece of software that can say, okay, well, informed to predict whether a new district is gerrymandered. But of course, what would happen if, for instance, like a bunch of Democrats all say, oh, well, it looks like they're going to use this app to inform what happens in the Tennessee election. So everybody in the Democrat Party, download this app on your phone and keep swiping right? Then all of a sudden, your machine learning tool isn't going to do very well, right? Because it's just going to tell you what you already have. Right? And so question of bias are quite important, right? We talk about this bias variance trade-off in machine learning quite a bit, that if you learn too much from your data, you might overfit, right? You might learn some of the uninteresting information. So what I'd say is I don't have a great solution to this problem, but it's sort of probably another sort of criterion I should add to my list, that when you talk about statistical methods, you better make sure your statistical input itself is useful.
You make cogent and clear arguments as to the complexity N of the problems at hand, but complexity analysis ignores the constant scaling factor. And what we have in hand in the US is not an unbounded problem. There is a maximal N of interest. Is it not possible that at some point improvements in the scaling factor will allow the maximal N to be attacked?
Well, I think it's possible, right? That's the problem. We don't actually know if P equals MP. Okay, so to address, I think there's actually kind of two different languages that are tangled together in this question a little bit. So when we talk about scaling factor, actually typically we talk about that as a lower bound, that we say, oh yeah, algorithms can run in n log n time. In other words, they kind of scale almost linearly in the size of your data, but in fact it's like 100 million times n log n time, right? We just kind of ignore that 100 million. Then it might be that things that look tractable actually aren't, right? That's typically when people talk about scaling factors, that's what they mean, and they're absolutely right. That's a consideration that's important. I think what this person is asking is actually on the other side, right? That in fact, there's like, for example, a finite number of congressional blocks, so these asymptotic arguments of like when n goes to infinity are actually irrelevant. I guess that's kind of true, but what I would say is that the number of blocks is so large that you're really in the regime where these asymptotics matter. I've never encountered, and this is a practical thing rather than a theoretical thing, I've never encountered an algorithm where the constant is so small that you can, like, yeah, it's it runs in exponential time, but in reality it's like 10 to the minus 11 exponential times an exponential time. I think that's very rare in the algorithmic world. But I invite you guys to prove me wrong, right? It would be excellent if it turns out these problems actually are solvable at the end of the day.
One last question. There are examples of small perturbations correctly making real difference in fairness. In states with laws that representatives must live in their own district, opponents have modified lines just to remove that person's house from a district.
Yes.
Have you thought about what kinds of small perturbations should be off your list of things to stabilize?
Well, I have now. No, like I mentioned in my talk, that's exactly right. I actually asked you guys that question, and I'm really glad to hear that one of our listeners was thinking critically. So this is a great example where, for example, this Frichet, or rather this Hölder property, incidentally, it's probably not the same Hölder as that Supreme Court case, is probably not something you would want. And absolutely, if we're going to codify any standard like that, we should enumerate any case where we really do expect this sort of discrete change to happen. And that's a good one.
Thank you very much.
All right. Should I introduce you?